Okay, welcome to week 10. So we'll be looking at a couple of post-graduation problems. So I'll post the problem to you, take some time to think and start solving, and then we'll together we'll solve the problem, okay? First I'll write it down in terms of words, okay? So the first problem is a flow or a flat plate problem, okay? Okay, so it's a flow or a flat plate problem. Air flows over a flat surface 2 meters in length oriented in the direction of the flow. Okay, so it is parallel to the flow direction and of sufficient breadth maintained at 150 degrees Celsius. Pressure is 1 atmosphere. Bulk air temperature is 30 degrees Celsius. If air velocity is 12 meters per second, determine the local heat transfer coefficient as a function of longitudinal position. Second part, the average heat transfer coefficient. And the third part, rate of heat loss from the surface. So just think about this problem, maybe refer to your class notes and all. And maybe after 5 10 minutes, we'll start solving it, okay? So just ponder over this problem, how to solve it. Okay. So for this portion, you can refer to any standard heat transfer book. Okay. Like Vinay Kumar Datta or JP Holman or something like say Ghosh Dastidar, etc. Right. So coming back to this problem, hope you had a crack at it. At least refer to your notes. I'll solve it anyway now. See, if you have referred to the notes in the class, you would have come across many correlations for the Nusselt's number. And Nusselt's number is just h into some length scale divided by k of the fluid. And from there you get the heat transfer coefficient. So before selecting any correlation, so you have to, it depends on what? It depends on Reynolds number. For laminar flow, it will have some correlation. For turbulent flow, it will have some correlation. And also the Prandtl number variation that also fits into this correlation. So first, let us do that. Okay, I'll just write it into in terms of words. Okay, as I said before, selecting the correlation for the Nusselt number, from where we can extract the heat transfer coefficient that is H. First, we have to find the maximum Reynolds number in that system. So our calculations for simplicity will be based on 1 meter breadth of the plate. So we are assuming that the breadth of the plate is 1 meter. Okay, what's the temperature of the flat surface? It is 150 degrees, right? And the bulk air temperature is 30 degrees. So what's the mean film temperature then? We can take the average of both. Okay, and at 90 degrees Celsius, you can refer to the internet or some uh, books like relating any standard textbook or some book relating to the properties of different fluids. Let's find the density, viscosity, everything at that temperature. You can even Google all these data. Okay. So at 90 degrees Celsius and 1 atmospheric pressure, the density of air is 0.962 kg per meter cube. The viscosity of air is 2.131 into 10 to the power minus 5 kg per meter second. Likewise, for Prandtl number, like what's it? Prandtl number is Cp mu by K, right? So you have to know Cp and K value also. K, that is the thermal conductivity. If you just Google it, you'll find that it is approximately 0.03. Okay, 0.031 watt per meter degree Celsius. Cp is 1.01 kg per kg degrees Celsius. Length already said 2 meter. Velocity, that is the free stream velocity, 12 meter per second. So what is Reynolds number? Maximum Reynolds number in the system possible. What's the maximum dimension here? The length is 2 meter, right? So what is Reynolds number? LV rho by mu. V we know, rho we know, mu we know. So get the maximum Reynolds number. Take at the extreme edge of the flat plate. 2 into 12. What is rho? 0.962, no? Mu 2.131 into 10 to the power minus 5. So if you calculate this, it will come to around 1.083 to 10 to the power 6. Random number is CP mu by K. Just plug in the values of CP mu and K and tell what you get. Random number. So you should get 0.694. Fine. So what's the correlation that has to be used here? So as we found out, maximum Reynolds number is at the end of the plate. That is at x is equal to 2 meter. And what does that indicate? It indicates that the flow is turbulent over there. So somewhere at the plate, the turbulence has to start now. So because at the starting point is x is equal to 0, so it will be like Reynolds number will be 0 only. And slowly Reynolds number will increase. And if you remember, the transition Reynolds number is 5 into 10 to the power 5 for flat plate. So transition to turbulent flow for flat over a flat plate, right? Okay. So at some point, the transition happens from laminar to turbulent. So at till some distance in the plate, it is laminar flow, and after that, beyond that, it is turbulent flow. So appropriate correlations have to be used to find the Nusselt's number, and from that the heat transfer coefficient. Because laminar flow will have particular kind of correlation, and turbulent flow will have another kind of correlation. Okay, so the heat transfer coefficient for laminar and turbulent flows over appropriate regions have to be used, and the local heat transfer coefficient should be averaged over the respective regions. But before that, we should determine till what distance the laminar flow holds and from where the turbulence begins. So that in the laminar region, we can apply the laminar correlation, and in the turbulent region, we can apply the turbulent correlation. So I'll put it in words. Say the distance is L prime. Okay. So what is the transition turbulence Reynolds number for that to happen? It's 5 into 10 to the power Faraday. So assuming that distance is L prime, V rho mu we know, right? What is V? Is 12. Rho is 0.962. Mu is 2.131 into 10 to the power minus 5. So from here, calculate L prime. You must get L prime equal to 0.923 meter. Fine. So let us denote the heat transfer coefficient in the laminar and turbulent regions by H prime and H. And just write it in words. X is the local distance from the leading edge. So I just write down the correlations for laminar region and for turbulent region, okay? Or maybe we'll solve them separately, okay? So just, I hope you have written the correlation somewhere. Anyway, I'll just write it again. You can refer to the class notes also. So for laminar region, okay, so for heat transfer in laminar boundary layer flow, the following correlation for the local Nusselt number can be obtained. So this equation is given in this book by Vinay Kumar Datta, page number 111. Okay, so there it says that for laminar region, the Nusselt number correlation is Nusselt number is equal to 0.332 into Reynolds to the power half into Prandtl to the power 1 by 3. So what is Nusselt's number? Nusselt's number is just here in laminar we have taken as H prime now. H prime X by K. So if you remember the difference between Biot number and Nusselt number which I told in the previous class, both formulas are Hx by K only. But in Biot number it is K by K of solid and Nusselt number is K of fluid. Okay. So this is 0.332 into what is Reynolds number for a distance x? Xv rho by mu to the power half. Prandtl anyway is constant only. Cp mu by K, that doesn't change with distance. Okay, so if you plug in all the values and all, you will get H prime is equal to 6.707. Just check if I made any mistake or not. Yeah, x to the power minus half. And what will be the unit of h prime? It will be watt per meter square degree Celsius. This is in the region where it is laminar. So x is less than or equal to L prime, where L prime is 0.923 meter. Fine. So this is our expression, h prime is equal to 6.707 x to the power minus half. Now let us look at the turbulent region. Here it is represented by h. Hx by k is equal to 0.0296 Rex to the power 4 by 5 Randall to the power 1 by 3. Now again substitute all the values. Reynolds number is just hp rho by mu. Randall is anyway constant. So here h you will get as 31.4 x power minus 1 by 5 watt per meter square degrees. And this is valid from 0.923 meter to 2 meter. Okay. So this was the first part of the question, the local heat transfer coefficient as a function of longitudinal position. So as a function of longitudinal position, you have one for the laminar region and the one for turbulent zone. Right? So now next part is what? Average heat transfer coefficient. That's it now. So yeah, B part, your average heat transfer coefficient has been asked. How do you think we'll get that? See, this is this flat plate, okay, 2 meters long. Till 0.923 meter, this is laminar and this is turbulent. You have one expression for heat here, you have another expression over here. So you'll just do an integral average, right? To get the H average, 1 by L over the entire length, 0 to 0.923. Use the laminar correlation, okay? 6.707 x to the power minus half dx. Then 0.923 to 2. Apply the other boundary condition, the other correlation. What was that? 31.4 x to the power minus 1 by 5 dx. So what will you get? Simple integration. L is what? 2. You just get from 0 to 0.0923, mean 0.923, 6.707 x to the power 1 by 2, whole thing multiplied by 2, plus 0.923 to 2, 31.4 x to the power 4 by 5, divided by 4 by 5 or into 5 by 4. Fine. So what's this value? 2 into 6.707 into x to the power half. X varies from 0 to 0.923. That's 31.4 into 5 by 4 into x to the power 4 by 5. This goes from 0.923 to 2. Just plug in the values now. You should get 22.2 watt per meter square degrees Celsius. Okay, very simple. Over the laminar thing, you apply the laminar correlation. Over the turbulent zone, apply the turbulent correlation and just do integral average of it. So what's the third part? Third part is the rate of heat loss from the surface. Okay, so what's our area of the surface? It's 2 meter, and I have assumed 1 meter breadth. So area is 2 meter square, and our Q will be just H into A into delta T. H will apply the average coefficient, average heat transfer coefficient. So it's 22.2 into 2, and what's the delta T? It's 150 minus 30 is equal to 120. So just plug in these values and you should get 5329 watt. Okay, so just go through these three parts once. Convince yourself about the process. Okay, even if you get different values, it's okay. But you should apply this kind of the concepts, the steps you should follow are these. Okay, just go through it for a couple of seconds and then we'll go to the next problem. Okay. Hey, hope there is no doubt. Okay, in this problem. See, funda is very simple. For laminar, you have some correlation. For turbulent, you have some correlation. But across the flat plate, where the air flows over it, till a distance, it will be laminar. Beyond that distance, it will be turbulent. So you'll have to apply two different correlations. One correlation for the laminar part and one for the turbulent part. Okay, so there are various correlations where you have to find the Nusselt number. Those are many of them are empirical or even by proof. So I've noted that also. You can also check the class notes or any standard book. Okay, so you get the heat transfer coefficient from those correlations. It will be a function of x. Okay, and that x can again vary. In the laminar zone, there will be some x, and the turbulent zone, there will be some other x. And from there, you can also find the average heat transfer coefficient by doing an integral average. And once you get that, you can easily find the rate of heat loss in the surface. Okay, so now we'll look at one more problem, and similar to this, I'll give you some time to think about it before we solve and discuss the problem. Okay. So our next case will be flow across a cylinder. Very common in chemical engineering, convective heat transfer in a flow across a cylinder. Like that, you can also have flow across a sphere. Some other correlation will come over there. Okay, but just clear your concepts here. I'll note down the problem first, then we'll talk about it. Okay, so I'll read the problem now. The 0.724 millimeter diameter nichrome heating wire carries a current of 8.3 amperes. The wire has an electrical resistance of 2.625 ohm per meter. Air flows across the heated wire at a velocity of 10 meter per second. If the bulk air temperature is 27 degrees Celsius and pressure is essentially atmospheric, what will be the temperature of the wire at steady state? Okay, so just think about it for a couple of minutes. Maybe even take 5 minutes. And approach will be very similar. See what correlations like we can apply. Like there is Fand correlation, Eckert and Drake correlation, Churchill and Bernstein, depending on different Reynolds number, etc. Okay. So just think about this problem for a couple of minutes and then we'll solve it. Okay. What is asked in this question? What's the temperature of the wire at steady state? Okay. So what does steady state means? That there will be no variation as a function of time. So that is only possible when the heat generated by the wire is equal to the heat that is convected out from the wire to the ambient. When there is a balance between those two, we can say that it is a steady state. I just write it in terms of words. Okay. So at steady state, the rate of electrical heat generated should be equal to the rate of heat lost from the wire by forced convection. And temperature of the wire can be calculated from heat balance. That's the unknown, right? And of course, for calculating the heat transfer coefficient, you have to apply suitable correlation. And in this case, it is cross flow across the cylinder, right? So let's take the basis as one length. The last time we took 1 meter breadth. This time let us take the basis as 1 meter length of wire. Let's take an assumption that the wire temperature is uniform throughout. Otherwise, it can be more, this problem will become much more complex. That's not the case. See, here the temperature of the wire is unknown. So what will you take the mean field temperature as? Right? That's a problem now because last time we had both the flat plate temperature as well as the ambient temperature, we took the average 150 plus 30 by 2. But in this case, what do we do? Okay. But temperature of the wire is unknown in this case. How do we resolve? So we have to approach this problem a bit numerically, okay? So we'll take the values at the bulk at temperature of all the properties. We'll have to do a couple of iterations in this problem. So what's the bulk at temperature? It's 300 Kelvin now. So yeah, like the previous problem, the pressure is also 1 atmospheric pressure. Note down the air properties at these conditions. Velocity of the crossflow is given as 10 meter per second, right? So what's the wire diameter? It's 0.724 millimeter now, or 7.24 into 10 to the power minus 4 meter. Surface area is pi dl. Basis you took as 1 meter now, so repeat that. Area is this. Current is what? 8.3 ampere. Resistance is 2.625 ohm. So what's the heat generated? It is pi square R now. If you remember electrical systems, it's just I square R. Maybe as I said, we'll have to go through some numerical calculations in this problem because unlike the previous problem, we don't know the temperature of the wire in this case. It's an unknown. We have taken all the properties at the ambient temperature and ambient pressure. Okay, so just let's calculate the Reynolds number in this case. We know the diameter of the wire now, so that T we will take. We know, rho we know, mu we know. Rho and mu based on the ambient temperature ratio. So this will be what? 7.24 into 10 to the power minus 4 into 10 to 1.777 by 430. What's Prandtl number here? Cp mu by k. This is Cp. Mu is what? It's 0.76. Okay. So based on this Reynolds number and Prandtl number, the correlation that we will be using is what is known as the Churchill-Bernstein correlation. So just write down that correlation once. 1977. Very big expression, okay? So this number is equal to 0.3 plus This symbol you never have to by heart, okay? You can just refer to these correlations and go on with your problem. Okay, this into this. And this holds true for Reynolds number falling in between the range 0.01 to 10 to the power 7. And when Reynolds into Prandtl is greater than 0.2. So both conditions are satisfied here. So just in this big equation, you plug in all the values. I'm not going to do that. Do it in your own free time. So the Nusselt's number that you will get here is 10.8. When you plug in all these values into this gigantic expression, which is nothing but hx by k. H is diameter of the wire here, hc by k. Or h is equal to 10.8 into k by d. Plug in all the values. Get 391.4 watt per meter square degrees Celsius. And what's the rate of heat generation in the wire? It's I square R, no? Any electricity textbook you open, you get that. Basis of 1 meter. It's what? I is for 8.3 ampere now. 8.3 square into 2.625 is equal to 180.83 watt. That's Q. And this Q, that is 180.83, is equal to H into V into delta T. Okay. H into what is A? 2.274 into 10 to the power minus 3. So delta T is unknown, no? H we know, 391.4. So from here, delta T you should get 203 degrees Celsius, which is the difference in the temperature of the wire and temperature of air. So temperature of air already we know now, 27 degrees. So temperature of air is for 27 plus 230. Earlier we did not know the temperature of the wire. We just assumed every property to be the ambient temperature property. But now we know what is 230 degrees. So now you do second iteration. Now we know the mean air film temperature. If we want 230 plus 27 by 2. So it's 128.5 degrees now. You repeat the calculations and you will get a more accurate estimate of the wire temperature now. So at this temperature, 128.5, I write down all the properties. At 128.5 degrees Celsius, rho is equal to 0.878 kg per meter cube. Cp is equal to 1.014 kilojoule per kg degree Celsius. mu will be 2.3 into 10 to the power minus 5 kg per meter second. K is 0.0338. So at using these properties, you get Reynolds number is equal to 276, Randolph number 0.714. Again, apply the correlation, that Churchill-Bunsen correlation, and you will get the such number as 8.47. Okay. And using all this, you just, if you do the same process and get H value, okay. Hx by k is equal to Russell number, na? So H value you will get. Take the calculations yourself later. $395. And this U equal HA delta T is equal to I square R. You do that. You will get what? 180.83 by 395 and equal to 201 degrees Celsius. Therefore, Y temperature is equal to 201 plus 27, 228 degrees Celsius. Last time we got 230, this time we got 228. So like that you can do the third trial, fourth trial, etc. Okay, third iteration, fourth, and you will see that it converges to almost like 230, 228, 229 degrees. Okay, so do it in a free time. Okay, so just go through this problem once more. Take a 2 minutes break and go through it. And if you have any doubt, none of you are present here. Okay, but anyway, just go through it for a couple of minutes, and then I'll just do one small thing and wind up the class. Okay, hope there is no doubt. So I'll just end the class in a couple of minutes by listing out some correlations. I won't write down the expressions of the correlations, but you can just treat it as a homework and investigate yourself. Okay, find out these correlations. Okay, so for instance, laminar flow in circular plate. These are all very standard, famous correlations. Okay, proven to be very effective over the years. Hausen, 1943. So some are theoretical, some are like experimental based. Nevertheless, you just have to know the correlations. Okay. So likewise, there is one for circular pipe. There is one called Cedar Tate, 1936. So the year that I'm mentioning, like that's the year when their paper was published with these results. Turbulent flow through circular pipe. Here we have British Coulter, 1930. Whitaker, 1972. For flow across a cylinder, you have Fand, 1965. Eckert and Drake, 1972. Churchill Bernstein, 1977. Whitaker, 1972. Likewise for flow past a sphere, you have Kramer's, 1946. Whitaker, 1972. Okay, so that concludes the class. Just have, when you're in your free time, just go through all these uh, papers and their correlations that are mentioned over here. That concludes the class. See you next week.